Okay, so as previously mentioned, my name is Marianne Bellotti. Most people know me based on this book I wrote about legacy modernization. I guess it's kind of a cult classic. People I do not know personally love to talk to me about it, so that's really, that makes me very happy and proud inside. I have about 20 years of software experience, most of which has been spent in the bowels of some of the oldest systems on Earth. And what I want to talk to you about today is this problem that I hear literally every single time I start a new project, which is I come in and they say, so we don't actually know what that system does or how to change anything on it. Or they say, there's this one guy that knows how this system works. And hopefully he won't leave or win the lotto or get hit by a bus or decide to retire. Is this a familiar scenario for anybody here? Like, anybody have a system like that where there's the one dude? Yeah, it doesn't, like, we find this a lot in old systems, but it's not exclusively an old system problem. I find it also with like very young organizations as well. Transferring knowledge between engineers is a big problem, right? And so I like to solve this problem with mental models, because I think ultimately how we think about systems are about mental models, right? And so before I get into the nitty-gritty details about that, I want to start off by clarifying what I mean by model, right? The model in this scenario, in this talk, is a mental model, which means it is understandable and storable within a single person's brain space, which also means it is not a full and complete model of the system itself. It's some little slice of the system or its behavior that has been simplified so that it is comprehensible to a human being. It's also, therefore, an abstraction that communicates a key concept about the system. Typically, it's an abstraction about expected behavior, the relationship between different concepts, or what are called invariants, which we'll talk about in more detail, which is a form of expected behavior, except it's the negative, the things you don't want to happen. The models we're not talking about today are machine learning models or AI models. There's lots and lots of conversations, mainly from vendors today, about these things, but that's not the session. We're not talking about AI models. Also, what we need to be appreciative of is because we're dealing with simplifications here, we're really kind of understanding that they're accurate up to a point. Like, they have a particular scope. They have certain conditions in which they're considered to be useful models. The word we use for this are axioms, things that are always assumed to be true within the model. And they might be dependent on specific definitions, in fact, as well. So these are not like data models we might use or declarative specifications we might use, where our assumption is that there's something of a one-to-one parity between the model and the implementation. We often have a large gap between the model and the implementation when we deal with these kind of mental models. So given all that, given the fact that it's not a one-to-one parity situation, it doesn't cover the whole system, it's a simplification based on abstractions we basically made up, like, why are they useful at all? Like, why should we use mental models? Well, with any system, we have a bunch of different parties that are involved in discussing and iterating and maintaining the system. We have yourself, we have your colleagues, we have the actual implementation that exists in production, and then we have kind of the environment that exists around that implementation. And all of these things may, in fact, disagree about what certain ground truth realities about the system are. And so we need to have ways of communicating our assumptions about the system and its operation to each other that allow us to, like, highlight those gaps and then close them as quickly as possible. And this is where mental models are really useful. They help find gaps in our understanding by allowing us to compare our understanding to each other. They allow us to transfer knowledge. They allow us to vet and refine requirements by often forcing us to get specific and strategic places. They generate scenarios and hypotheses about systems that we can then test and verify. And most importantly for this talk, they help train your intuition about systems. So you already use things within software development that take the form of mental models. For example, class inheritance is an abstraction that we make up to sort of communicate how we see the world within our source code, right? Unit tests, same thing. We're looking at behaviors, what should happen, what can't happen when we write unit tests. Then we have data schemas, which again are an abstraction, kind of sorting the world and the universe into particular formats for us. And then lastly, we use mental models a lot with triage. Whether we know it or not, when we triage, we're using mental models of systems. So that's what I felt was like the most relevant thing for SREcon to kind of focus on, is like what happens in triage with our mental models. And so this is what we know about how experts use mental models, or how experts triage, right? They have this kind of robust library of very simple models. Most experts don't have like the all-encompassing universe perfectly like articulated. That's what everybody thinks that is going on in the expert's mind, is that they have this incredible Miro board of like everything that's ever existed within the system all spelled out. But in actuality, experts tend to have like these really small, simple models just in bulk. They have a lot of them. And they're coming into the incident and the triage session, and they're kind of trying to observe what's going on and very quickly match what's going on, what they're observing, to the closest, most useful model that's in their little mental library of models. And then when they have that closest possible match, they do predictions on it. They run that model forward. They go, giving what I'm seeing and this model, what will happen? Or they run that model backwards. Given what I'm seeing and this model, how did we get here in the first place? But while they're doing this, they're also continuing to make observations, continuing to consult that library of mental models, continuing to make predictions. And so it's this endless cycle of like going to the library of mental models, making predictions, doing actions or other diagnostic activities based on those predictions to either validate them or rule them out, and then making more observations, and so on and so forth until triage is complete. And so people tend to form mental models of systems by operating them. And that's why it's so difficult to transfer knowledge. It's because the best way to build mental models about systems is to operate the system, and that takes a really long time. Typically, the process kind of goes like this. We spend a little time operating the system, absorbing the normal state, then something awful happens, there's a huge incident, we panic. While we're panicking, we're also kind of recording all the things that are going on and building more models of like how things could fail. Presumably, we solve the incident, we go back to a normal state, and now we have both models of what normal looks like and also models of what failure looks like and the different sort of things that could go wrong and what caused them. And so mental models tend to be about behavior, so we build them by observing behavior, and incidences are the most effective model generators. But it's hard to put people in a situation where they're going to deliberately run into incidents. It's hard both, you don't want to have incidents, also it's rather stressful to just throw people into incidences as quickly as possible. So engineers also tend to form models by exploring systems, and sometimes that's feasible, just letting people sort of read source code and like play around with things in a staging environment. But it's usually not very effective to build models via reading documentation. And so this is funny because this is very counterintuitive for a lot of people. When there's a situation where we're having trouble onboarding people onto new systems, transitioning knowledge, usually people go, if only we had better documentation, all of these problems would be solved. And documentation is valuable, but documentation often speaks to a completely different set of needs than the mental models you use in triage. So again, mental models focus on behavior, what could happen, what must happen, which are often called properties, what should never happen, which could be called invariants or constraints. And then within that, we kind of give some examples of how this manifests in real-life software engineering. We have unit tests that define what could happen or must happen. We get a little bit more sophisticated. We can maybe use fuzzing or property testing and extend that to like what should never happen. And then we can get even more sophisticated than that and do specification, where we're looking at like logically, do all of our assumptions about the system even make sense, right? Or are there obvious conflicts? Other type of mental models that we use are based on analogy, which admittedly is a bit of a strange term to throw in a technical context, right? Like, what do we mean by analogy? And so analogies are really great because they back our instincts about systems. There's some analogy-based models are properly called heuristics. I'm going to use those two words interchangeably. They're probably not technically interchangeable, but the idea being that they're patterns that we're matching about systems. So we look at one system and we think that it's like another part of the system for some reason or another. Maybe the same person built them, maybe they're written in the same language, maybe we worked on one part of it one day and another part of it another day. There's something about this that we establish a commonality between, and we use it to make really quick, logical, deductive reasonings about the impact of incidents, about where to go next within the middle of a triage. And so they can be extremely effective and they can be extremely useful. It's where a lot of that like, aha, I'm a wizard sort of insight tends to come from, but they can also lead to errors if the relationship in question is not relevant, in fact relevant at the particular time. So some examples of this, like let's suppose we have a security vulnerability that's found on one of our libraries. Like now we have to sort of in the process of figuring out how to resolve this, we have to go, well, how many parts of our system use this library? Right? Are they all impacted by this vulnerability? What impacts are likely to be the most serious? These are the sort of questions we have to ask ourselves and the information we have to gather as we're sort of figuring out how to resolve this. And so these are places where a lot of the time an engineer will be sitting there and going like, oh, well, I see that this is a Node package and like these are all the places we use Node, and so these are all the places that could be affected, and then like narrowing it down. And that's what I mean by analogy. Truth be told, this particular example, we could probably solve this via some sort of fancy static analysis tool, right? Certainly, we could run a scan, figure out where all those libraries are all throughout our stack. But realistically speaking, a lot of organizations don't have those tools. And if those tools aren't present, or they aren't configured correctly, or for some reason, and I don't know why orgs keep doing this, only security gets to look at those tools, not engineering for any reason whatsoever, then you have to kind of fall back on other strategies. You can't always solve these sort of situations with tools. So I'm going to circle back to documentation, because I kind of hit a low blow as saying like you don't really build great mental models from documentation. I did want to explain what I meant by that. So documentation sort of emphasizes things like, what does the system look like? Architecturally, where is everything? How is everything connected? How do I interact with the system as the user, right? What are the commands? What are the endpoints? How will the system interact back with me? What are the errors I might get? What's the responses I get? Things like this. These are the sort of things we express with documentation, and they are useful, but you should notice they don't actually describe much in the way of system behavior. They talk about what the system looks like and give you an idea of how to anticipate types of responses, but what's going on under the hood is not usually something we cover a lot in documentation. And so these things can be very useful in triage, right? Because it's broadly useful to figure out like what technology is in play and what is it talking to. That's really great. It's really useful to know like kind of logical system boundaries, like how does the organization think about beginning and end points within a complex system. It's also really useful to figure out how components are sort of grouped together. Like, does the same engineering team own two completely different things? Sometimes the answer is yes. That's useful to know because it tells you more about what types of things you're going to see on each part of that system. One thing that sometimes is misleading is that sometimes it can suggest information that's not actually in the documentation at all. So I find I have this problem all the time where people assume that a given service is a private service because it happens to be positioned here in the architectural diagram instead of close to where the little person graphic is. Meanwhile, there are ports all open all over the place, and you can just dial in for the public internet whenever you like, right? So there are some misleading things from documentation, but we do get some good insights that are sometimes useful. And the interactions, it's good to know what sort of things I can do on a system and what sort of things are allowable in the first place. It's a good place to start. But one of the big advantages we get from documentation, if people have had the foresight to sort of include it in documentation, is design intent, which is essentially like, why did we build this thing this way? Why does the team that owned the system own the system, right? What other solutions did we consider, and like why did we reject them at the time? And these give a lot of sense of both like system behavior and the relationship between systems that can be very useful. So let's talk about how triage works in a little bit more detail. This gentleman up there is one of my favorite safety science researchers, Gene Rasmussen. I knew I was going to trip over his last name. And so specifically, he wrote this paper that I'm a really big fan of called Mentor Procedures in Real-Life Tasks, a Case for Electronic Troubleshooting. And what he did in this research paper is he gathered a whole group of maintenance workers and set a system problem in front of them and asked them to triage it with what we would today refer to as a user researcher sitting right next to them. And every step of the way, the user researcher was kind of writing down what they were doing, asking them questions about what they were thinking about, why they were doing what they were doing. And then at the end, they sort of aggregated all of these sessions and looked for patterns in how expert maintenance workers interacted with systems and resolved problems on them. And they found them. They found like 3 main search patterns that experts use when they're triaging systems. I'm going to do a real short plug here because I have a little pet project where I'm annotating my favorite social science papers, including that one, online. So if you want to read the paper with my commentary about why it's important for software engineers, you should check out Tech Should Know. That concludes my brief commercial break. Thank you so much. So going back to this, search strategies. Topographic search, right? So topography is about the arrangement of physical features. You think of the map where we see where the inclines are and the declines are. And so a topographic search is essentially tracing a signal, a transaction, or a request through the physical components of the system. Now, today, physical is kind of like has to be a little bit more flexible than it was in the past because we have a lot of virtual infrastructure and like most people don't really have a sense of like where the transaction is moving throughout AWS's data center, nor do they need to. So we can be a little bit vague around the restrictions around tracing it through the physical components of the system, but essentially we're talking about architectural diagrams, system boundaries. Can we follow something all the way through everything that we think it touches? Functional search is a little bit different. We're focusing on places where we know that the problem could be because we know the problem involves a certain type of functionality. So if we know that the problem is that our data is coming out of our request corrupted, then the first thing we might do is zero in on all our data stores and things that interact with data stores. Is it in fact corrupted within the database, or is it good within the database and at some point it leaves there and ends up gibberish? Right? Same thing with like you have a connection error, you probably don't start immediately from your application code, you probably start with like DNS and like your certificates and all of those things. You are basically doing a filter on where you know the components of your system actually perform that function. And then the last one is fault evaluation. And this is where we do a lot of our analogy type thinking, where it's like a functional search, but it's more specific to the actual system in question, because we're connecting an observed behavior to specific locations where we know that that behavior either takes place or is impacted in some way. So we know through our experience with operating the system that there's something relevant about this part of the system based on the behavior that we are observing. So now that we've kind of gone through the landscape of different types of mental models and search spaces, let's figure out like how you actually build these models proactively. Let's start with topographies, right? So one of my favorite exercises to do with engineering teams is just a process map, essentially. Like I sit with them and I say, let's pick one task on this system, one transaction. Let's start with how it begins, and let's go through step by step. How does it move through the system? Like what happens where? And we just basically build out a process map. It's surprisingly effective because the immediate result is you get a whole bunch of I say, what happens next? And they go, well, at some point it ends over here. And I'm like, yeah, but what happens next? And we have this big question mark. So we start to expose where the unknowns are, or where people are unsure about things, or where there are active disagreements about things. And once we know where those unknowns are, where those disagreements are, then we can now make the assignment, okay, this is a list of things that we kind of expose through this exercise. Go figure out what the real answer is, right? So it's a topographic search, and the real benefit of doing this kind of exercise, it gives people practice with doing topographic searches throughout their architecture. And it also, you can do counterfactuals with it, which is one of my favorite things to do. So let's suppose we have this scenario. We're submitting a form. The value of one of the variables in that form will change the behavior of the system. If it's true, then it processes the inputs. And if it's false, it just returns home back to where you are, right? And so an example of what a counterfactual is would be I'm running this session. They explain these steps to me. And I ask, well, what if x is nil, right? And that leads to the next question, which is what would cause x to be nil? So this is an example of a counterfactual. It's a hypothetical that's not true that you kind of treat as if it is true and make sort of a scenario up from there. And the great thing about this type of reasoning and having a process map in which you're doing it on is that, again, you can trace this forward and backwards. We can take the first question of, like, x is now nil. What happens to the system? Like, at what point do we end up, right? Is the behavior of the system different? Does something crash? Does something bad happen? But then we can also trace it backwards. X is nil. Is it possible for x to be nil? What would have to happen for x to be nil? And so again, this starts to expose things that people haven't thought about in terms of how their systems behave, open questions, gray areas, and starts to bring it to light so they can actually figure out what the answers are to these questions. And so some best practice is about running this kind of session. So that one guy who knows everything about the system that everybody is afraid is going to leave doesn't get invited to this session. And he doesn't get invited to this session because people learn really best by exploring and learning for themselves and discovering knowledge for themselves. They do not learn via information dump. And I find, particularly among software engineers who are very, very, very concerned about ever looking wrong about anything, that when you put the guy who knows everything in the meeting, you just end up with like a 20-minute TED talk from the guy that knows everything about the system, which might be very useful, but actually won't result in much absorption of knowledge. It's really important to allow people to confront what they don't know and kind of guess what it could be and then verify those guesses. And so the goal of this exercise is not to end up with a beautiful, complete process map of any particular part of the system. The goal is to expose those questions, to expose those unknowns, and to give people like one thing they can do to know the system better than they did before. And so in this process of like going forth and trying to answer those questions and unknowns after the meeting, I have a real clear rule around what an acceptable answer to those unknowns are, and that is ground truth is sacrosanct. So if you are truly at a loss for how to find the answer to that question, you can go to the expert that knows everything. You can consult them for guidance, but you need to bring me back ground truth. And ground truth means I need to see logs with the evidence that the behavior is occurring. I need to see source code with like where the behavior happens. Or if for some reason we don't have logs and we can't find where it is in the source code, then anything that's like of the moment, contemporaneous notes like postmortems, RFCs, ADRs, Slack threads, PR comments are probably good enough to sort of establish ground truth. The reason why this is more valuable than like the guy who knows everything told me so is because I can actually link this to a particular moment in time. So if this information is 5 years out of date, at least I know it's 5 years out of date, right? So if we can't find logs and source codes, then we can go by contemporaneous notes. But I want people to actually verify information that they're getting rather than just accepting like rumors about how systems work. Because often even our best experts are wrong about what system behavior actually is. OK, so moving on to developing our analogies about systems. This is called a mind map. And when I was first exposed to mind maps in like kind of the non-business school that I went to. I went to a school for nonprofit management. So it was like business school, except way more complicated. And I did not take it particularly serious. And then one day I found myself working with an engineer who was just extremely good at triage. And as I was talking to him about how he thought about things when he was looking at like incidences and pages, I thought to myself, oh God, everything is based on like just these word associations, essentially. Like I saw this, I know this library is being used over here. Like those analogies. And I was like, shit, we have to mind map. That's the only way I'm gonna be able to record this information. And so this is the kind of session where I do invite that wise expert to kind of like riff on how they associate different concepts, different terms, different types of code and infrastructure, and so on and so forth. And what's really interesting about running these kind of sessions is that you can sort of flesh out defined and undocumented relationships. Like, why do we associate this with this, right? Like, what's the backstory behind that? And then the other thing that's really interesting about this is that everybody's going to have a different mind map because there's no right or wrong way to form analogies and associations on systems. And so we can sort of compare what different levels of experience look like, how they associate different parts of the system. And that can be really interesting as well. Like a relatively new person on the team might see a very simple relationship, whereas a relatively experienced person on the team might see something way more complex and nuanced. Okay, so taking a slight change of pace, how many people work at organizations that have SLOs? Great. Keep your hand up if your organization actually uses SLOs to make product roadmap decisions. Oh, look at all the hands going down. Yeah, so like what's really funny to me about SLOs is there's such a great like decision-making tool in terms of how we prioritize new product features versus maintenance, right? Like that's the whole concept of an era budget is like how much leeway do you have before it starts negatively affecting customers. And yet so rarely are they used that way. Mostly we just use them as another thing to alert on and then page engineers in the middle of the night on. And so in my quest to solve this problem, I started using our good friend Rasmussen's, another model from our good friend, a functional boundary diagram. Actually, this is called a couple of different things. I call it a functional boundary diagram. My engineers are currently calling it the crazy eye diagram. Has anybody seen this diagram before?
I call it the fish.
Yeah, the fish. I like it. I like it. So fun fact, the talk immediately after this, I think, is actually a deep dive on this diagram. So hopefully this is a preview and not a spoiler. But what's important to understand about this diagram is that the top boundary is we go completely bankrupt. We've run out of money. The bottom, slightly to the right boundary is all of our engineers burn out and quit. And then the one that curves around on more of the left side is the product actually fails. There is actually that dotted boundary on the slight inside of the left because they did acknowledge that often the technology is broken long before people realize the technology is broken and we just continue to use it anyway. But what I like is really the only thing you need to sort of appreciate about this diagram from my point of view is that it makes kind of a rough triangle or I suppose fish-shaped area. And what I can do with my engineering teams is I can say like, okay, here's a dot representing this service or this system, whatever we're talking about, whatever context we're in. Which line is your service closest to? Are we closest to completely running out of money? Are we closest to everyone quitting because they're so overworked? Or are we closest to having so many problems with this service it falls apart? And we can have a conversation about that as an engineering team. Like, where is this dot within this area? And then as we discuss different things that we can prioritize in the development of this system, we can then have a conversation about how those various things might move this dot. And what I like about doing this, and the reason why I call it baby SLOs, is because it emphasizes trade-offs in how you prioritize what work you're doing and when. And it gives you the same type of thinking we're supposed to be doing with SLOs, but it doesn't require any data. It doesn't require any like fancy logging. It doesn't require any numbers. A lot of times, SLOs are really difficult for people who've only ever been in engineering orgs where they've inherited them. Like they were already set, and they're just panels in New Relic or Grafana in their dashboard. And they don't have to think about like what is the customer impact of this. Like, where is the appropriate level to set our SLOs? A lot of times I'm dealing, because I deal with legacy infrastructure quite a lot, I'm dealing in places where there's no historical data. So we have absolutely no idea what the performance of this system has been like at any time, and therefore have no reference point on like what good performance is versus bad performance. So there are lots of reasons why real SLOs may be difficult for people, and this allows them to sort of get into the habit of thinking that way about them, which I find is really useful. So kind of just looking at this in terms of maturity of the organization. Phase one of using mental models is finding gaps in our thinking with models. Phase two of using mental models is forming hypotheses about our system that we can sort of test and verify and explore with using models. Phase three is about proving that our ideas about our system in fact make sense to anyone other than ourselves. And for this, unfortunately, we require computers. So if you get far enough along where you feel comfortable sort of thinking about how your system behaves in terms of steps, and then thinking about what the behavior that must happen in that particular function or service in order for it to be considered healthy is, and what the type of behavior that should never happen is, when you get used to that kind of thinking, you are like a hair's breadth away from writing an assertion about that behavior. And there are a number of really amazing modeling languages and specification languages that are designed with the idea that if you can express yourself in this way, if you can write about things in terms of states and steps and properties and invariants, then they can explore the state space for you and tell you if any of the things that you are asserting must always be true, should never be true, and if you really want to be fun and advanced, you can do should be true eventually, and things like that. They can actually tell you if those things are correct or if there's a flaw in your underlying thinking. And so sometimes this can expose some really fun, complicated bugs that are just kind of lying in wait in the system. Most of these things are based on first-order logic, and I do other talks and workshops about this in more detail, but I will spare you the math talk. And so, like, the kind of important thing to understand about bringing computers involved in this is that, like, a lot of times people try to start from this point rather than building up the discipline and the maturity around thinking and mental models. And of course, the first thing they say is like, this is great. I'm going to write a specification of my entire system, and then everything's going to be proved, and then everything will work forever. Or, even better, they say, this is great. I'm going to write an entire specification of my system, and then I'm going to figure out some way to have the code automatically generated, perhaps through ChatGPT, from my specification to like whatever its code is, and then I'll never have to worry about anything again. And it's important to, again, emphasize that the larger and more complex the system is, the larger the gap between the specification, the model, and the implementation can and will be, because mental models are, again, simplifications and abstractions. And so it's really way more important to build the strong discipline around critical thinking and talking to people and like comparing notes rather than jumping straight into let's prove it all correct, because it's actually a lot of work to prove it all correct. So I have a little bit more time than I thought I was going to, which is great, because now I can go on and talk about a little bit more about model checking and how it works in detail. Does that sound good to you guys? Oh, I see lots of head nodding. All right, great. Okay, so I'm going to take you through kind of like a quick version of how I teach people to start thinking about modeling in such a way that you can run it on a computer with a model checker. And the way I like to think about things is in terms of state machines. So I might look at an architectural diagram like this. This is a sample, like a toy architecture diagram my friend did that I should probably give him credit on the slide, I suppose, but hey, que sera. So I might look at something like this and say, okay, we have a breakdown of components because we have a simple architectural diagram. Each of these components has a state machine. So can we agree on what the states are in the state machine and how they transition from one to the other? Like just roughly, how do they transition? That includes how they might trigger state changes in other components. And so I actually break this down into like a simple swim lane diagram. I like to keep it to 3-4 lanes tops. Again, simple, not better than complicated, simple, always better than complicated with this. So I like to have like 3 lanes of components that interact and kind of look at like how states transition across these lanes. If I can do that, then I can look at those transition points and ask myself, okay, what causes us to go from processing to dispatch at this point? Like, what is the logic within the system that triggers that transition? And if I can express that as in, like, if this is like that, then we transition to this state. If it's not, then we stay in the state that we are. That is the thing that can now be formally verified. And so that's generally how I get from point A to point B on this. But again, the most important thing is to kind of start with those basic mental models, build up that strength and that discipline, and then work your way up to getting more and more advanced and more sophisticated. So to wrap things up, mental models, they power our intuitions about systems. You are using them even if you never take any of my advice or do any of the exercises I have talked about in this talk. You will use them all the time. You build them automatically, mostly through your operation work, operating a system. But you can build them intentionally by mapping out your understanding of behavior and the patterns in the system, and then comparing it to other people's models of behavior. And so some of the model strategies you can use right now, they don't involve any fancy technology. Your log story can be a complete mess. You just need a whiteboard, possibly a piece of paper. You can use process maps. You can use mind maps. You can use functional boundaries to help start having conversations about how the system is operating and how to make decisions on it. And then when you're ready and you feel good about that, for deeper practice, you can start investigating computer model checking and sort of move into that wonderful world. So that concludes my formal talking points. I know I'm happy to take questions in the time we have left.